Hello everyone, my name is Oriol Angurell. I'm a scientific researcher in the Leitat Technological Center from Spain. I've been working here for the last 3 years, and now I'm the scientific coordinator of the Nefertiti project. Here in chapter 1, we will see the challenge of the photochemical systems and how we approach it into this project, the Nefertiti project. So, we will first discuss different photochemical systems, different photochemical reactions, and which is the CO2 role nowadays. Then we will present shortly the consortium of the project, and we will see the general and specific objectives and how we approach it with the methodology. So, as we all know, nowadays there's a big problem with CO2, contamination, and all this stuff. So, nowadays all the projects aim to do is to reduce this amount of CO2 to make greener processes, greener products. So, we have to keep in mind that we need to reduce the amount of CO2 that is produced, and one of the ways to do it is if we can use it as a reagent to transform it into something that has some added value. We will be at the same time reducing the amount of CO2 and transforming it into different products. So, how we can relate this with photochemical systems? First, we will see different examples of photochemistry. Photochemistry basically is defined by chemical reactions that are catalyzed by light. So here we can see 2 different examples that I won't enter into details, but if we can at the same time transform this CO2 using the sunlight, we will do a really green and sustainable process. So here is when Nefertiti appears. The main goal of Nefertiti is to transform this CO2 into ethanol using only the sunlight as the energy donor, let's say. So we will try to do that during the project, and now we will see how we can do it. Before that, I will show you briefly the consortium of the project. Nefertiti project has 10 partners. We can see here different partners from Spain, from Ireland, from the Netherlands, from Turkey, from Cyprus, and then we also have partners from Peking and from Michigan. The project will end at the end of 2025, and the duration is 48 months. So once we have presented the consortium, we can see here a general picture of the project, a general scheme, and here it gives us an idea of what we will do. So as we can see here in the bottom picture, we can see that our reagents will be hydrogen and CO2. We will flow them into a first reactor and transform it into hydrogen and CO. Then, after this first reactor, we will go into a second step to transform this syngas into ethanol. We will have different units here, as for example, oxygen removal, membrane purification, and other things that we will see. But this is the general picture of the process. Try to make a compact approach to transform water and CO2 into ethanol using only an integrated device and using the power of sunlight. So, looking more into details into the specific objectives of the project, we will, apart from using this photocatalysis that I've talked you before, we will have the help of other things. For example, first we will use different photosensitizers that will help us to concentrate the light and increase the efficiency of the process. Then we will also have an oxygen system removal in order to avoid different explosive mixtures. And we will also have a membrane unit purification to purify the ethanol that we obtain. So with all these helps, we will try to increase the solar to fuel efficiency, the selectivity, and the performance of the system. And the main goals of the project are to achieve and scale up the process up to 10 milliliters per minute, validate it indoors up to 1 to 5 days, and then validate it outdoors for 5 hours in continuous mode. Okay, so how we will do it? The first technology that we have here in Nefertiti, and I think it's a key point, it's flow technology. Flow technology will help us, for example, to continuously remove the oxygen that is generated in the first reaction, and with that we will avoid explosive mixtures in the second reactor, so we will ensure the safety of the process. Another good part of that is that with flow chemistry, you know that we have really small microchannels, so the light will be more efficient in that microchannels than in a big batch reactor, so we will overcome irradiation issues. Then another key part of the project, I think, is the photocatalyst. We will develop two different photocatalysts, one to transform CO2 and water into syngas, and the other one to transform this syngas into ethanol. So the first photocatalyst will be based on a 2D COF system that will be doped with different metals, such as gold nanoparticles, ruthenium nanoparticles, and this will help to perform the reaction in a very efficient way. And the other one is the second photocatalyst that will provide us the CO reduction at the same time that we perform the CC bond formation to obtain the ethanol. So in this case, it will be a Fischer-Tropsch catalyst doped with also different metal oxides, for example, titanium oxide, iron oxide, and sometimes maybe iron carbides, so that we will be able to achieve this ethanol in a very efficient way. Finally, we will have also an extra help, as I said before. For example, here we will have light harvesting systems. In the first case, we have luminescent solar concentrators that are normally organic dyes and are persistent luminescent materials. So we can see here at the right part of the picture that we will have the sunlight. We have the sunlight with all the spectrum of the wavelengths. And if we can find a material that can absorb, for example, let's say at 400 nanometers, and can emit at 600 nanometers, and our photocatalyst absorbs at this wavelength at 600, we will be concentrating part of the light into the ones that we want to tune the photocatalyst and to activate it. So this will be an extra help to increase the efficiency of the system. This material will be deposited at the external parts of the reactor by different coating techniques. And finally, we will have also optical devices. We will have a lens system that what we will do is concentrate physically the light. We will prepare two different lenses that can concentrate the light in the reactor, so we can increase the power of the light that we will have in the system. Finally, where we will do it in two different reactors. At the top right part of the picture, we can see the smaller ones. It will be the same for both, for the first and second reaction. We will perform and optimize the system there. These are really small reactors, I would say like chips more or less. You can see here the height of the reactors and the maximum flow rate, which is really small. We will test this system with xenon lamps, and once we have tested this system in these small scale reactors, we will scale it up into these bigger ones, and we will be able to scale it up to 10 times. So apart from that, we will also aim to test the system outdoors using sunlight. So this is a general picture of the project, and then in the following chapters we will discuss more into detail the insights of each part of the project. Thank you everyone, and I hope you enjoy the course and learn a lot.